So the next unit that we're going to study is chemical kinetics. And to start off this unit, we're going to talk a little bit about this idea of a rate of a reaction and reaction rates. So when we talk about chemical kinetics, what we're talking about is how quickly a reaction will proceed. What we've been doing up till now, when we talked about the energetics of a reaction, we've talked about the reactants and the products, the relative energies. We talked about the change of enthalpy that occurs as you go from reactants to products, but we haven't really concerned ourselves with how quickly that is done. And so how quickly that can occur is what we talk about with chemical kinetics. Now, this has nothing to do with whether the reaction will proceed or not. We'll get into that later on in the course when we talk about Gibbs free energy and entropy and spontaneity. But assuming a reaction will occur, whichever way will be spontaneous, we can talk about how quickly, or at least study how quickly that reaction will proceed. Okay, so this is really interesting. What we're looking at is that arrow, so when we have some chemical reaction, A plus B goes to C, it's this arrow. What's occurring in that arrow part of this chemical equation? And this is something that that's temporary. It doesn't last for too long, and so we don't put it in our final chemical equation, but it's an integral part in going from these reactants to the products. And it involves things like the transition state, this temporary transition state going from reactants to products, the energy that you need to get up to the transition state, and just this whole mechanism. What's this pathway that is followed as we go from reactants to products. So the area of kinetics is kind of this middle area. It's the part that we've been kind of ignoring up until now as we're just talking about the change of enthalpy. So when we study kinetics, because things like the transition state are very temporary, what we tend to do is we look for the things that we can actually see, and that is concentrations. We look at concentrations of products and reactants and how they change over time. And there's a few ways that you can do this, but probably one of the more popular ways to do it is by using spectroscopy. So if you have a reaction or product that absorbs a certain wavelength of light, and very often this is going to be like a visible light, right? If it absorbs a certain color of light, we can check to see how that absorbance changes over time. And because of Beer's law, you guys remember Beer's law? Because of Beer's law, that concentration correlates directly, the absorbance correlates directly to the concentration. So if we track the absorbance versus time, that'll be the same as if we were tracking concentration versus time. So looking at these graphs of concentration versus time, we can use those graphs to study the kinetics of a chemical reaction. So a lot of what we're going to do in this chapter is we're going to be looking at graphs of concentration versus time. And so these are kind of what these graphs look like. Now, this is not experimental data. This is some mock above it. But it's for this reaction where we have hydrogen gas and we have iodine gas, and those are going to form 2Hi gas. Okay, so this is one of the first reactions, the simplest reactions studied. This was studied using femtosecond spectroscopy. It was very cool. But again, looking at this idea of a rate of reaction, how we can quantify that rate, what we can do is we can say, oh, okay, well, if we plot concentrations versus time, then for every substance in this reaction, we can think about how its concentration is changing in a given amount of time. And we'll define that as the rate of reaction. So if I want to write the rate of reaction for this, I could do this in a few ways. I could say, okay, the rate of reaction. And by the way, this rate of reaction will always be in terms of molarity per second. It's concentration per time. We use molarity, we use seconds for time. So it's going to have units of molarity per second. And I could say that this is equal to the rate of disappearance. Now, something about the rate of reaction is we always want it to be positive. The concentration of hydrogen will be going down over time. So this delta concentration of H2 is going to be negative. So I'll put another negative sign out here to make the whole thing positive. So I could say it's equal to that. Okay. Or I could also say it's equal to the change in concentration of I2 over time. Or, and this is going to be a little weird, what I can say is if I'm going to define the rate of reaction based on the change in concentration of H2 and I2, then to make all this equal, because I'm making 2 molecules of HI for every 1 molecule that's used up of the hydrogen and the nitrogen, I say that this rate of reaction is only going to be 1/2 of the change in concentration of HI over the change in time. So again, a lot of guys, what they want to do is they want to put like a 2 here, right? They want these coefficients to go there. Kind of a quick way to remember this is to take these stoichiometric coefficients. So there's a 1, there's a 1, there's a 2. So you just kind of divide these rates by stoichiometric coefficient. So this would be divided by 1, this will be divided by 1, and then this, the 2 goes down here, it's divided by 2, and that kind of helps keep it all straight. But this is how we define reaction rates. Again, we could define it in terms of any of these 3 species. We do tend to standardize it. Whichever species has a 1 in front of it, we kind of use that as the baseline, and we refer everything to that. And also make sure that your rate of reaction is always positive. So for any reactant that has a concentration that's decreasing with time, then we're going to have to put a negative sign in front of that when we express rate of reaction. And that's about it. And in class, we'll do a sample problem and see how this all works out.